Calculus, we're looking at section 4.9, antiderivatives. So this is leading us up into chapter 5, where chapter 5 starts relating more integrals and our properties within there. So if you think about it, for every function that we generally have, we have some sort of inverse function that exists that we start working with. And that's where the antiderivatives come in. Talk about that inverse of our derivatives as we start going through. So if we look at our definition here of the antiderivative. Okay, a function f is an antiderivative of f on an interval I, provided that f prime of x equals f of x for all x in that interval I. So basically what we're talking about is we're talking about that we have our original function. So we have our function, and we took the derivative and we got our other function here. Now we're going to be going back to it. So one of the things that we really have to reference in here is there's a major issue with antiderivatives, okay? A major issue. So basically kind of bringing it up to this theorem 416 right here, the family of antiderivatives. So let f be the antiderivatives of f. So cap f is the antiderivative of lowercase f on the interval I. Then all the derivatives of f and I have the form cap f plus c, where c is some arbitrary constant. So if you remember, whenever we took a derivative, so if we had our little function f and we had whatever function's going on, it had maybe a constant here. When we took the derivative of that constant, it was 0, so it zeroed out. So now in our derivative function, we don't have that. So now we got to take it back in, and that's where this plus c comes in. So basically here they kind of give some graphing scenarios of this, okay? So they kind of talk about, well, our derivative function is, but we could have any alternating. All we know is the slope at which we're talking about with that derivative. So we don't know where we're at on this, because once again, we don't know what that original function had for that plus or minus any constant that would be in that original function. So once again, some rules. First rule we talked about is a power rule, that if the integral, so we basically start talking about the antiderivatives as an integral. Now there are two types of integrals. There's an indefinite integral and a definite integral. Okay, indefinite integrals just deal with the variables and the overall functions. Definite integrals we'll talk about more in the next chapter in the application that really comes into play with definite integrals. But in our indefinite integrals, we look at just our function itself. So it says, if we're going to take the integral of x to the p dx, it equals, well, we're going to add 1 to the exponent and then divide by it. So if you think back, when we took the derivative, we multiplied by that, and then we took 1 away from the exponent. Well, we got to go the opposite. We have to add 1 to the exponent, then divide. So when we took the derivative, we multiplied. So if I just quick grab a sheet of paper here so you can kind of see what's happening on this. Remember when we had, let's say, x to the n, okay? If we took the derivative of this, so if I said let's calculate the derivative of x of n, we would take n and then we would subtract. So we would multiply over, then we subtract 1. Well, what happens here is if we're going backwards, okay, if we're going backwards, we want to now work with this function by adding 1 here. So we would have x to the n power, and then we would divide by whatever we added in here, in which you notice n over n is 1, so we have x to the n. So you see the derivative took us to this. Then by performing, let me go like this, the integral of x to the n minus 1 dx, once again this is our derivative right here, we would take this, I better go like this, proper notation, we always want to be proper with our notation, take the derivative of this, so we have this, so once again the derivative equals with that dx over here, so that's why that dx comes down here on this. The integral then would say, let's add 1 to this exponent, so that's where n, and then divide by that, so n over n, so we get back here. So if you notice, the derivative took us here, the integral of that took us back to what that original equation was, and that's where this is really going towards. And then we just have a whole bunch of theorems. Now, a lot of our theorems in here are going to be more common sense, okay? Trial and error, we should be able to think about it. Next chapter, we will get in depth into proper notations, formulas. How do we work with more complicated problems, okay? So we talked about the constant rule. Once again, like when we took the derivative, we could factor out that constant, take the derivative, then multiply that constant back in. We can do the same thing with our integrals. We can simplify the function by factoring out a constant and then going there. We also have our sum and difference ones here that we could take the sum or difference. I'm going to toss that difference in there as the additive inverse in here. It could be a minus sign, so this could be a minus sign right here. Where we could separate them out and perform the integrals separately as we go through. We have our trigonometric expressions. Remember we had all those formulas for the derivatives in trigonometry. Well, now we're going to start going back. Once again, do realize that when we take the integral, so here we talk about the derivative of sine ax equals a cosine ax. Now, once again, if we have cosine of ax right here, and we want to take the integral back, we have to take one. Once again, they're applying kind of that chain rule that when you take the derivative of this, you're going to have to multiply by the derivative of what's inside. But remember, there's always this plus c. Okay, so there's always this plus c. So it's something actually I forgot, and I'm going to come back and add that into my notation here, just because I better be proper with this. We should have that plus c right there as we're kind of referencing everything in here. Remember back in our power rules, that natural log, we looked at the derivative of the natural log x is 1 over x. So if we have 1 over x, we're going to go back to that natural log x. Once again, the plus c. Because we don't know if there was some constant in that original function that when the derivative is now given, we don't know what that value would be in there. More formulas. Okay, so here we got a whole bunch more formulas as we start going through. Some of them involve our e. Let me see if I can get this a little more visible for you. If I go e to the ax equals a e to the x, well, now we're going to take that integral. Once again, just kind of giving a formula here. B to the x, once again, the derivative was b to the x, natural log x. So if we consider back here, these are some little bit more complicated ones that we'll be working with. So do be well aware that there is a whole formula in the back of the book, sheets upon sheets on it. Let's see here if I can not lose my spot and get you to that. Okay, so here we are in the back of that book. Once again, integral tables. Notice we have a whole bunch of integrals and different integrals in here, or trigonometric integrals. We come over here. We got our reduction formulas for trigonometric functions, integrals in there, integrals involving a squared minus x squared, so on and so forth. We have a whole nother page here. So there's pages upon page, well, 3 pages I should say, right here that really kind of delve into it. Once again, if you remember, here was all our derivative ones. Now we're taking everything backwards. Because we're taking everything backwards, one of our main problems that we kind of work with derivatives was our standard position formulas. So if we had something moving along a standard position, and then we want to figure out the velocity, we would take the derivative to find what the velocity was of that function. Then once we knew the velocity, we could take the derivative of that and then move into our acceleration. Well, now we're going to start considering the fact that suppose we're moving along a line that a known velocity is from here. Then its position is found by the initial value problem. Once again, the derivative of the function equals v of t. So s naught equals, or so s sub 0 equals s naught, where s naught is the known initial position. And then once again, velocity t equals our acceleration. So we're going to start looking at some problems kind of going backwards. So if we just kind of see here, basically we know that the derivative of the velocity or acceleration is negative 9.8 meters per second squared, because once again, that's a very common number, once again, for gravity, because gravity decelerates at 9.8 meters per second squared. And then we might know an initial velocity, but we might not know the function at which we're traveling. So that's where we know that if we take the integral of this, or the antiderivative of it, we would have this right here, that plus c, and then we would start substituting numbers in to find our value, or our v of t. Once again, I'll show you an example on this and how we take it down then to the standard position by taking the integral once more, substituting in, to basically find our original standard position formula. So this is where things really start taking a turn. We have the derivatives, we know how to work with the derivatives, we know what the derivatives tell us, but now we're going to look at, well, what about the antiderivative? What about if we inverse these? How do we go backwards, and how can we tell what those meanings are, and what applications do those have? Now, those applications really take in depth into Chapter 5. Once again, we'll be defining this more or better for you, okay? So as of right now, this is a little bit more common sense, basic formulas that we'll be going through, kind of trial and error, be able to think about both ways. Next chapter, we will have to dive deeply into what the actual formulas are and knowing how to use those formulas.